So in class, we did a quick little activity where cohort A came up with a combination of small and large bows that would make them at least $60, and cohort B came up with a combination that would not earn them at least $60. We did a little spreadsheet activity where we saw the graph kind of divided in half, where the points all were located on one side that made us 60, and on the other side were the points that did not make us 60. This is going to help us graph our inequalities today. So the first thing we're going to do is we're going to just determine if the ordered pair is a solution or not. And the simplest way to do this is going to just replace x and y in the inequality. So in example 1, I'm going to replace x with 10 and y with 3, and I'm going to see if my answer is less than or equal to 6. So I would get 10 minus 9, which is 1. And yes, 1 is less than or equal to 6, and so that means that yes, the point 10, 3 is a solution to this inequality. Similarly, on example 2, I'm going to replace y with 2, x with negative 1, and I'm going to see if this makes the inequality true or not, which would get me 2 is greater than 3, and since 2 is not greater than 3, then no, the ordered pair negative 1, 2 is not a solution. So here's a table just outlining some differences between equations and inequalities. So of course, equations have equal signs, while inequalities have inequality signs. The thing about an equation is that only the points on the line would satisfy that equation, and nothing else. With an inequality, you can see that both of these have a shaded region. So in both cases, the points within that shaded region will satisfy the inequality. Now in the case of less than, or even if it was greater than, you're going to see a dashed line. And so this is similar to how we graphed an inequality on a number line using an open circle. We want to go up to as far as this line, but we don't want to include the points on the line as part of our solution set. So the dotted line is simply a boundary line. In this case, only the points in the shaded region would satisfy the inequality. In this case, since the line is solid, this is similar to a closed circle, which means we're going to go all the way up to the line and include it. And so this time, the points in the shaded region, as well as the points on the boundary line, would satisfy the inequality. So now we're going to get into the graphing. So the first thing we're going to do is, given whatever the inequality is, we're going to graph it as if it were an equation with an equal sign, and we're either going to use slope-intercept form or x and y intercepts, and we want to be efficient. So on example 1, since it's already in slope-intercept form, I'm going to graph this as if it were the equation y equals mx plus b. I'm going to get my points on the graph. Then I'm going to choose a solid line or a dotted line, similar to how I choose an open circle or a closed circle. So what that means is that if the inequality is greater than or less, we're going to choose a dotted line, and if it's greater than or equal to or less than or equal to, we're going to choose a solid line. Then we're going to shade one side by picking a test point, and hopefully we can choose the point 0, 0. If not, we can choose something else. So on example 1, since my y is already isolated, I'm going to graph this using slope-intercept form, which means I'm going to start at my y-intercept of negative 3. Then I'm going to rise and run my slope, which is 4 over 1, and I'm going to do that as many times as will fit. Now if this were just an equation, I would take out my ruler and I would draw a line. But before I do that, I want to look at my inequality, and since I see that it's greater than, I know that that means I'm going to draw these with a dotted line. Now I should still use something straight like the edge of a piece of paper or a ruler or a binder. Unfortunately, I explain everything, that's kind of difficult. But again, the dotted line shows that this is my boundary line, but the points on the line itself would not satisfy the inequality. My last step is to pick a test point. Now in this case, the origin is not on my line, so it's available to pick. And remember, the coordinates of the origin are 0, 0. So just like we did previously, I'm going to see if the origin is a solution to this inequality or not. Y is greater than 4x minus 3. And to do that, I'm going to replace both y and x with 0. And hopefully you can see why the origin is such a great point to pick. It's pretty easy to work with. So then I would get 0 is greater than 0 minus 3, which is 0 is greater than negative 3. Now that's true, which means that the origin is in fact a solution. And here's the origin. It's located on this side of my boundary line. That means all the other solutions are also located on this side as well. So I'm going to shade in this side, and I'm going to go right up to my boundary line. And so what this inequality represents is that any point from this shaded region, but not on the line, would satisfy this inequality. If the origin were not available, which would only happen if the line itself would pass through the origin, you can pick any test point you want. Just make sure you're replacing x and y with the correct coordinates when you do that. Let's jump to example 3. On example 3, since this one is in standard form with x and y on the same side, I'm going to graph this as if it were the equation x minus y equals -1, which means I'm going to use x and y intercepts. Remember, to find an x-intercept, I change y to 0. If I were to change this to 0, my equation would say x equals -1. And if I were to change x to 0 to find my y-intercept, this would say -y equals -1, which means y would equal +1. Now before I connect my line, I want to go back to my inequality, which is greater than or equal to, and this means I'm going to connect with a solid line. So this time the points on the line are part of my solution set. My origin is still available to pick as my test point, so I'm going to go back to my original inequality. I always test in the original, and I'm going to replace x and y with 0 and see if it produces a true statement. And that's going to get me 0 is greater than or equal to -1, which is true. That means the origin is in fact a solution to this inequality, and it's on this side of my line. So I'm going to shade this side as well, going right up to my boundary line. And so this time, any point within the shaded region, as well as along my boundary line, are solutions to my inequality. Pause the video to try examples 2 and 4. Press play when you're ready to check your answers. So on example 2, I graphed this using slope-intercept form. Since y was isolated, I started at a y-intercept of 1, and then I rose 3 and ran 1. I did some points in the other direction as well, just to give myself more points to connect. Since my inequality was greater than or equal to, I connected with a solid line, showing that the points on the line are part of my solution set. And then I used my test point of 0, 0 by replacing x and y both with 0 to see if it produced a true statement. It produced a statement 0 is greater than or equal to 1, which is not true. That means that the origin is not a solution, which means none of these points on this side would be solutions, meaning they must be on this side, so I shaded in the other side. For example 4, since this was in standard form, I graphed it using x and y intercepts. To find the x-intercept, I changed y to 0. That would give me x equals -8. Remember, I'm graphing it as if this were an equal sign for the time being, so my x-intercept was -8. To find my y-intercept, I made x 0, which means that to get y by itself, I had to divide by 4, and since -8 divided by 4 was -2, that was my y-intercept. My inequality was less than, so that tells me to connect with a dashed line. And then my test point was 0, 0. So if I change x and y to 0, I ended up with the statement 0 is less than -8, which is not true, which means that solutions must be on the opposite side from 0.